Hello everyone and welcome to the next discussion which is related with techniques to generate digital elevation models. This is the second part. One more part we will have later. In the part 1 we have discussed mainly various types of techniques to generate digital elevation models. And in the first part also we focus after that we focus mainly on how we can employ survey toposheets to generate digital elevation models employing the spatial interpolation technique of GIS. But here we are going to focus more on how this radar remote sensing can be employed, and then we will see that what are the limitations and what are the advantages. So, as you know that this your digital elevation models can be generated various ways. We have already discussed these methods, and this is what we are going to discuss, the either stereo pairs, CARTO sets or other things, and radar sets. So, in this particular discussion we will focus mainly on the employing this radar data. Or first before that about the employing stereo pairs also. As you know that for this you need optical remote sensing images, and which are acquired by the satellites, and employing then using that photogrammetric techniques we can develop digital elevation models. And for example, there are various satellites, though the journey started using stereo pairs and generating digital elevation model with the SPOT, but SPOT is no more in space. So, there are various other satellites which are providing, and like for example, our IKONOS satellite or QuickWord satellite, they can generate digital elevation model at 2 to 5 meter resolution. Now, Pleiades 1A and 1V constellation, they can allow us to generate 1 meter resolution, but it is currently very expensive data. WorldView 2 and GeoEye 2 also, and they can allow us to generate digital elevation model at 1 to either 2 meters. So far, whatever these satellites which I have discussed, you have to buy the data, and which is very expensive. So, unless it is really required to have a digital elevation model at 1 or 2 meter resolution, then one should think of employing the stereo pairs of these satellites for generating digital elevation models. Whereas one should try to resort to the free data like ALOS data or Indian CARTOSAT data or French satellite 5 to 10 meter or ASTER data which is 15 to 30 meter. In many cases we have found through our practical experiences that even 30 meter resolution, spatial resolution digital elevation models are quite good. And if you go for 30 meter spatial resolution digital elevation models, then there are various options which are available to us, starting from SRTM-DM, and that is also available as 30 meter, ASTER which is also available as 30 meter, and then our CARTOSAT for entire India is freely also available at 30 meter. Though if you buy the data and process it using photogrammetric techniques, you can definitely create a digital elevation model at 2.5, but that will cost. So, if it is possible, and then or you can go little bit on 15 meter if it is available free, because if someone is working in a project which covers a large area of the earth, then it would be really very expensive to buy unless it is required. If it is not required, why to employ that one? Now, like in case of SPOT, how these stereo pairs were used is like here the example is given that on day 0 it was acquiring the same part of the land as 5 days before or 5 days later or 10 days later. So, if you are having multiple coverages of the same area with different angles, then generating stereo pairs is not difficult. And once you are having good stereo pairs without any cloud cover differences between two pairs or two photographs, then it becomes much easier to generate a digital elevation model. And this is what on the right side you are seeing, that this is how the digital elevation models can be generated employing this technique. But I also mentioned in the previous lecture that our Cartosat does not look sideways, it looks fore and after, means in forward and after mode, and in which you do not have to wait for another overpass to get the to complete the stereo pair. Stereo pair is generated within few minutes during a single overpass. So that was the biggest innovation was done in case of stereo pair generation towards development of digital elevation model. Further on this spot, satellites, the oblique viewing capability, that is very much required because the same terrain has to be recorded with two different angles. Then only a 3D perception would develop, and then that one can be used to generate digital elevation models. So, like employing a spot stereo pairs panchromatic images, this is another point. These stereo pairs are when we go for digital elevation models, they are always used in panchromatic, that is in black and white. So, this is Mount Pinatubo of Philippines, which is for that image we are acquired, a pair was acquired, and then you see a digital elevation model was generated using the same. So, not a big difficulty here. Similarly, that once you are having a digital elevation model, and if it is possible, if you can drape a satellite image over it, then you can create a really the 3D perspective view, which will give you a good feeling about that area. So, it becomes much easier once you are having a digital elevation model. Now, I would like to discuss Cartosat, which is what I have been mentioning, that it looks forward and after backward at the same during the same orbit data acquisition. So, when it keep doing like this, and then at the same almost at the same time you are getting data, and the differential cloud cover or other meteorological conditions will not have any significant role, whereas in case of spot it was real challenge to get in both photographs or one single stereo pair completely identical meteorological conditions. But in case of Cartosat it is possible. So, they have employed two cameras, one near Nade looking, that is -5 degree, and other forward looking, that is +26 degree, and providing the real time stereo data along track the spatial resolution of 2.5. The images, optical images may be of 2.5, but when you generate a digital elevation model, you may not end up with the same spatial resolution. You may end up with little lower, that means maybe 4 meter, maybe 5 meter spatial resolution. And this is what we did from these stereo pairs of Cartosat for our area of interest, and generated digital elevation models without any problem. So, this can be done. Many software supports these photogrammetric techniques, like for example, ERDAS, which is having a separate extension or suite, which is called photogrammetric suite, and using that suite you can definitely generate digital elevation model even using Cartosat data. And the same Cartosat data can be used, like for example here Cartosat 1 data of 2.5 meter, and this pen aft ortho image is draped over the digital elevation model which was generated by Cartosat of the same area. So, likewise you can generate. Now, there is also some other data is also available, which one can compare with the different areas, even they are might be having a same spatial resolution. So, this is what I was saying, that 30-meter spatial resolution in many cases, except for a very small area and one would like to cover in much detail, then one may go for higher spatial resolution. But otherwise in many studies, 30-meter resolution, spatial resolution of a DM is quite optimum. Here the comparison is between SRTM DM and ASTER DM. Why this comparison here in this discussion is because SRTM DM has been generated, ASTER DM is generated based on the stereo pairs, and whereas SRTM is generated based on SAR interferometry. That means two different techniques were employed for an area like Arunachal Pradesh of India. And if you visually you compare, you do not see any much difference here. But if it would have been a high hilly terrain like Western Himalaya, where you are having snow covered or glaciers areas, then this SRTM DM may not give you very good results because of the problem with the absorptions of energy and dielectric constant and other things related with radar technique, radar remote sensing. So, there where when you download the data, if they have not filled the voids, you may get lot of voids which would represent through, but would be represented through the no data. Whereas in case of ASTER, that issue does not come. So, in comparison also we have found that ASTER is quite good for highly rugged terrain like Himalaya, whereas SRTM DM, I am talking about the same 30-meter resolution DMs from both these techniques. Whereas so SRTM DM of 30-meter resolution may not be good of Himalayan terrain, but it is very good for plain areas. So, depending on your requirements, if you are working in a highly rugged terrain, then these stereo pair based technique or stereo pair based DM will be more accurate than your SRTM, and vice versa in case of plain area. Now, one powerful technique that I said in the beginning, so before that we discussed the stereo pair based technique, and now we are going to discuss this SAR interferometry or INSAR based technique. That is, it is becoming really very powerful and very accurate as well compared to other techniques. That is why it is very popular nowadays. And this SAR interferometry techniques for generation of digital elevation model basically started with the satellite which is called RadarSat, because that only allowed to create a pair, not a stereo pair, but a radar pair, and that then later on using this interferometry technique, digital elevation models were prepared. However, nobody tried to employ either RadarSat or Terra or NVSat ASAR or the Sentinel to generate digital elevation models for entire globe. Only it started with SRTM, Shuttle Radar Topographic Mission, and later on by this ASTER. And both of these the organizations which we are involved for these missions or satellites, they developed digital elevation models at different resolutions and covering almost entire globe. So that really brought a really paradigm shift in case of availability of digital elevation models at global scale. So, first of all, they provided the choices of different spatial resolutions, one, and also different DMs developed based on different techniques. So, that way though ASTER DM, as we have discussed, is based on stereo pair, but nonetheless some Stereo pair data is good, as I have also mentioned, for a hilly terrain like Himalaya, and SRTM is good for not so highly rugged terrain and plain area. So in that way, these are complementary. These products are really complementary to each other. So nowadays, lot of choices there, and this NV said earlier, now Sentinel data are available, and many of NVSat and Sentinel data, these are available free. So one can download the data, that is the radar pair, and can employ this SAR interferometry technique and can develop a digital elevation model of a relatively very high resolution. We have mentioned many times or discussed this SRTM, that is Shuttle Radar Topographic Mission. It was a mission, not a regular satellite, and the best part was, very innovative part was that one the baseline is a big issue in SAR interferometry. So what they had a 60 feet shaft which allowed to create a baseline. So there were instrument here and there were instrument here, and both were collecting the radar data or the radar information, and that means the same time with a fixed baseline, because baseline was connected with a shaft with two instruments. So with fixed baselines with two different angles, the same area was covered at the same time, and that allowed to generate a digital elevation model for almost entire globe, a relatively easy way than as compared to other techniques. Similarly, because RadarSat was a regular satellite, and therefore it did not carry that shaft of 60 feet, and so because you have to wait for another orbit to acquire the data, adjacent orbit, and sometimes the gap used to be of 35 days, and that means in these 35 days a lot of ground changes or weather changes can occur, and these changes will ultimately may be reflected in form of errors in these products. So these were the problems, but that problem was like in case of Cartosat stereo pair data acquisition, the problem of changing environmental conditions or meteorological conditions was resolved. Similarly, in case of Shuttle Radar Topographic Mission, that was resolved. But in normal way of conventional way of collecting data with two different angles of the same area, either using RadarSat or SPOT or any other satellites, these changes in the weather conditions brings a lot of problem. 35 days time difference is too big. So like here, this is the we call as power image, that is images in microwave region or radar images, and they say pair, a stereo pair or just a pair I would call, and when you can employ this these two radar images and can generate a digital elevation model employing SAR interferometry technique. Similarly, we also employed like instead of RadarSat, we employed a ALOS Pulsar DM and could generate a 12.5 meter resolution, and this is from Gujarat area or Kutch region. So as you can see, this is digital elevation model of the same area. The top are this is false color composite, top left. This is the power image, that is the radar image, and then you are having a digital elevation model generated with a pair using SAR interferometry technique, and you are also seeing a shaded relief model or hillside with colors. Now, if you look the terrain with the multiple spatial resolutions DM of the same area, you may notice the changes in the information content, or like here, this is SRTM 90 meter of the Kutch region, Gujarat. This is SRTM of 30 meter. This is Aster DM or GDM it is called, a 30 meter, and then ALOS Pulsar is 12.5 meter. So you can see differences, like here in 30 meter you do not see the details here as much as details you see in 12.5. So I would repeat that if there is a requirement, then only one should go for higher and higher spatial resolution, either for satellite images or for digital elevation models. If your requirement can be fulfilled with relatively medium range spatial resolution like 30 meter, then one should resort for 30 meter. Because in case of 30 meter, there are various choices are available. But in case of as you go higher and higher, then the cost may come. Otherwise 30 meter spatial resolution DMs are available free of cost, just you have to download from different sites. Now another technique which we have touched while discussing different methods of generating digital elevation models which are remote sensing based. So this is a new development which has taken place in last 7-8 years, that is the light detection and ranging, or in short we call as LiDAR. So again this is a remote sensing method which uses light in form of a pulse laser to measure ranges, variable distance to the earth. When the survey is being done by LiDAR, you do not basically see the light because it is in the form of pulse, just a very short illumination, and these light pulses combined with other data recorded by airborne system generate precise 3-dimensional information about the shape of the earth or its surface characteristic, that is basically a digital elevation model. Earlier it started with ground based radars, it used to be installed on a vehicle and so on. Now this and the instrument is going airborne or spaceborne. Now topographic LiDAR or generating a digital elevation model, basically it uses a near infrared laser to map the land, not really a visible light but a near infrared, because it has to cover a large distance from space to the earth. So it has been found that infrared laser is better when distance is involved than simple light. Now I would show you some examples of this LiDAR products, like here you are seeing here that the top left image is just that LiDAR image from top, or another viewing LiDAR image, and whereas in comparison you can also see a visual image in profile form and a profile generated from your LiDAR image. So this top left is basically LiDAR which reveals the and the top down, whereas the bottom is the Bixby Bridge which is seen here, and here definitely top right what you see a survey on the ground which has been done or photograph was taken. So in real the right one is the visible part, whereas the left one and the bottom left is your based on the LiDAR. Here you where from whatever the distance you are standing, you can also measure the distance as well as you can map the things as shown here. So basically LiDAR provides a opportunity to make high quality digital elevation models, because the number of points, or it is called point clouds, the number of points which it collects is enormous compared to any other technique. So you do not from spot height point of view, the density of points is very high. And if you are having, as mentioned while discussing interpolations using survey toposheets point heights, as mentioned that when you are having a high density of points, observations, measurements, obviously your digital elevation model is going to be very accurate because this is what your interpolation techniques require. So as you know that in this LiDAR technique, it first generate the DSM, that is digital surface model, which we have also discussed earlier in earlier lectures. So not directly first a digital elevation model. Now by masking that surface features sometimes as per requirements, we can remove that surface features and can get a bare surface, and that becomes your typical digital elevation model. So, the trees and buildings and canopy, which is when it is included in our data, then it is called the DSM. But when it becomes the bare earth or bare ground which contains only the topography, and the frequently called or better known as a digital elevation model. So, here on this image what you are seeing, the hillside representation of first return surface or DSM, and when this these features were removed like tree canopies and buildings or any other human made structure, then you get a pure DM, digital elevation model, or the typical digital elevation model which we know. So, you can see the major difference between a DSM on the left image and a DM on the right image. So, this DSM term basically has also come in this domain, which is the LiDAR one. Also here, if you can see very very carefully, you would find lot of red dots which are present on the left image. These are the nothing but the points which have been collected. These are the hundreds of LiDAR points, or we call as point clouds. So, when input is inputted, density of input points is very high, you can really generate a very high resolution, very accurate digital elevation model, and this is what it is shown on the right image. So, that is why LiDAR is becoming very popular, but we do not have any product which is available free of cost based on the LiDAR technique. Otherwise, it is a very powerful technique to generate digital elevation models or a 3D surface even on the ground at very high resolution and very accurately employing the LiDAR technique. Now, if we compare two digital elevation models generated using different techniques, like this is called 10-meter resolution. So, whereas this is 12 feet meter resolution, this is 10-meter resolution of the same area, and this is based on the contours on the left image, whereas this is based on the LiDAR. LiDAR, as you can see, can bring lot of details in this one. Now, only problem which you might have observed that if this is because removing the canopy and buildings, that means the creating a bare surface for a typical digital elevation model in case of LiDAR may not be always possible or may not be always complete. And that is why you are seeing some human made structures even in this bare LiDAR DM. So, that may be one of the problems associated with LiDAR DM. Otherwise, it can produce a very high resolution digital elevation model without much big problems. Another example here is this is this NED 10-meter. These products are not available for at global scale, only for US. So, this is 10-meter resolution and this is LiDAR at 1.5 meter resolution, and you can see that what kind of details it is providing on the right side image compared to a 10-meter resolution, and which is not based on the LiDAR either, the NED one, NED one. So, this kind of detailing is provided. However, as I have mentioned that even it is very difficult to remove all surface features or man-made structures or natural canopy completely from that surface. So, still it is not qualifying as a typical digital elevation model, but it is in between a DM and DSM. To some extent the surface features have been removed, for example in this one, but still they are many, their remnants are still visible clearly in a very high resolution digital elevation model. So, this brings to the end of this discussion, that is the second part of generating digital elevation models, using remote sensing based or some like interpolation based techniques. And in next part we are going to discuss also the thermal remote sensing based technique to generate digital elevation models. But for time being, thank you very much.